Welcome back. In this video, we are going to solve example 3.1 that is taken from chapter number 3, Mechanical Properties of the Materials, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement of the problem is a tension test for steel alloy result in stress strain diagram as shown in figure 3-18. Calculate the modulus of elasticity and the yield strength based on 0.2% offset. Identify on the graph the ultimate stress and the fracture stress. So you can see this is the tensile test specimen and tensile test is conducted, and as a result the stress strain diagram for this tensile test is shown over here. This is the real tensile test stress strain graph, while this is the magnified stress strain diagram till this region. Clear? Because you can see here we cannot identify the strain values, therefore they have given the magnified stress strain diagram till the point of yielding, and their strains are given in the blue color data. These are the strain for this till the point of yielding. So you have to determine the modulus of elasticity and the yield strength based on the 0.2% offset. Identify on the graph the ultimate strength and fracture. So let's start with the solution. So first we will find the modulus of elasticity. So I will write modulus of elasticity, and this modulus of elasticity can be obtained from the slope of the initial straight line of the graph. So you can see this is the slope of initial line of the graph that is exaggerated or magnified. So using magnified curve and scale shown in this blue color text, this line extends from point O to A and to estimated point A dash. This is magnified line. So which has coordinate of approximately, the coordinates are on x-axis. The coordinate is, you can see this blue color 0.0016, and on y-axis the coordinate of this line OA line. Let me choose this black color. This OA line, the coordinate will be 50. Y coordinate will be 50. So the slope of this line will be equal to modulus of elasticity, and this modulus of elasticity will be equal to y coordinate, which is 50 ksi. So 50 ksi divided by the x coordinate, which is 0.0016, and it is given in inch per inch. So when you calculate it, you will get the modulus of elasticity of this stress strain curve comes out to be 31.2 into 10 to the power 3 ksi. So this is the modulus of elasticity. Note that this equation of line, we can also write equation of line OA will be sigma is equal to 31.2 into 10 to the power 3 multiplied by strain. This will be the equation of line OA. How? Because we know that equation of line is y is equal to mx plus c, where y here is represented as stress and x represent epsilon. So m is slope, m is equal to slope, and the slope of this line is, we have calculated as e, and c is the y-intercept. Here c is equal to 0 because you can see it start from the origin. So from this equation, if I put y as sigma, m is e, and x is epsilon, and c is equal to 0, so this will be this equation, and e is 31.2 into 10 to the power 3 multiplied by epsilon will be the equation of line OA, which is the same over here. Now what will be the yield strength based on 0.2% offset? So let me write it. Yield strength based on 0.2% offset. So 0.2% offset means that it is 0.002 strain. Clear? Okay, this is strain, 0.002 strain. So what you can see here, that if I choose this 0.002, which is this one, this is 0.2% strain that is already given at this point. So from this point, if I draw a line that is parallel to line OA and draw a line, so it will intersect this stress strain curve at this point, which is called A dash. Clear? So I will write it at A dash. So now you can see that this will be the yield strength approximately. I will repeat. For a 0.2% offset, we begin at strain of 0.2% or 0.0020 inch per inch and graphically extend this line parallel to line OA till it intersect the stress strain curve at point A dash. So the stress at this point will be yield stress, and you can see here this is 68 ksi. So we can write that yield strength is equal to 68 ksi. Okay. Now in second part, we have to identify on the graph the ultimate strength and the fracture strength. So I will write ultimate strength, and we know that ultimate strength is the maximum strength that the material can bear. On stress strain diagram, you can see the maximum strength or stress will be at point B, and this is equal to sigma u, which is 108. So I can write it sigma ultimate comes out to be 108 ksi. And the last one is fracture stress. So I will write fracture stress. So the specimen is strained up to a maximum of, you can see here, 0.23 strain, and at this point the material fails. So you can see the stress related to the maximum strain, and at that point fracture occur. So this stress is fracture stress, and that is 90 ksi. So I can write it as fracture stress is equal to 90 ksi. And these are all the answers of our this example 3.1. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 3.2 that is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement is the stress strain diagram for an aluminum alloy that is used for making aircraft parts is shown in figure 3-19. If a specimen of this material is stressed up to 600 megapascal, determine the permanent strain that remains in the specimen when the load is released. Also find the modulus of resilience both before and after the load application. So you can see this is the stress strain graph for this aluminum alloy, and a load of 600 Newton is applied. So when it has been asked that when this 600 load is removed from the material, find the permanent set or the permanent deformation in this part. Also find the resilience for both before and after the application of load. So let's start with the solution. So first we will find permanent set. So when the subject is subjected to the load, you can see the load is applied. When you increase the load to 600, so the strain, it will strain harden until the point B is reached on the stress strain diagram. Now if you remove this 600 load, it will not come to the original point because it has crossed the yield point. So what we will do is that it will, from point B, if you draw a line parallel to this line OA, so it will go down to the point C. Now you can see this line BC and OA, they are parallel, so they are having same slope, and slope of this line will be the modulus of elasticity, and we can find this modulus of elasticity E for line OA. This modulus of elasticity can be found by stress over strain. So stress at point OA is 450, so I can write stress is 450 megapascal, and strain is equal to, you can see this is 0.006, and that is millimeter per millimeter. Clear? So just plug in the value. So 450 megapascal divided by 0.006 millimeter per millimeter will give you the modulus of elasticity. E will be equal to 75 gigapascal. So since both lines have the same slope, so line BC will also have the same modulus of elasticity. So what we are going to find out, we are going to find out the permanent set, because when you release load of 600 Newton at point A, it will go down to this point C. So this will be, this amount of the strain will be there, and this is the permanent strain, and we call this strain is strain OC. Now the total strain till the point of B, or the relative to the load of 600, the strain is 0.203. Clear? And we are going to find out this will be our permanent strain. Clear? So our permanent set. So we can write from the from triangle CBD, we require this CD. Clear? And we can also write that E will be equal to, E for this will be equal to stress is 600 and strain is this one. Clear? Which is CD, which is not known. So I can write it will be equal to BD divided by CD. So from here we are interested to find out CD. So CD is equal to BD divided by E. Now BD is equal to how much? BD is 600 megapascal divided by E of E is 75 gigapascal. So I can write 75 into 10 raised to power 9 Pascal, and you can also write this in Pascal, 10 raised to power 6 Pascal divided by 75 into 10 raised to power 9 Pascal. That will give you CD. Okay, so when you calculate, you will get this CD comes out to be 0.008 millimeter per millimeter. What does this CD means? That when you remove this load of 600, so at this point the strain was 0.023, and when you remove this 600 load, so instead of going to 0, it will go to this point C. It means that this CD, or this much of strain, is recovered elastic strain. So we can write it as recovered elastic strain, while this strain will be permanently available in the material. So this is also known as permanent set. So I can write this CD is equal to recovered elastic strain. Now the strain, this strain represents the amount of recovered elastic strain. So the permanent strain will be equal to this total strain, which is 0.023 this is the total strain. So this will be 0.023 minus, if you remove this recovered strain, which is CD, and that is equal to 0.008. Clear? So we will get 0.0150 millimeter per millimeter, and this permanent strain, which we call is epsilon OC, is the permanent strain that will be remain in this material even when you remove 600 megapascal load from the material. So this is the answer of our this first part. Now in second part, we have been asked also find the modulus of resilience before and after the application of load. So what we will do is that also you can say that, if I will write it over here, note, if gauge marks on the specimen were originally 50 millimeter apart, then after the load is released, the marks will be 50 millimeter plus 0.0150 times 50 millimeters, which means that the marks will be 50.75 millimeter apart. What does it mean? That, for example, if this is the specimen and there are 2-point marks on it having a distance of 50 millimeter, and when you apply a tensile load of 600 megapascal, so definitely the length of these 2 points will increase. For example, it will comes to a new point, to this point. So when you remove this load, for example, this is the new length, which is anything. Clear? When you remove this load, so it will not go back. This point, new point, will not go back to its original position. Instead, it will go somewhere there. Clear? So this is the original length, and this much is the strain is produced in it. And this strain will be equal to 0.0150. Our change in length will be 0.150 multiplied by 50, and that will be 0.75 millimeter. So after the removal of load, this point will still away from this original point. So it will be now at a distance of 50.75 millimeter apart. Now our second part was for modulus of resilience. So before and after, so I will find this modulus of resilience. So modulus of resilience is represented as small r. For initial, it will be equal to 1/2 stress for proportional limit into strain of proportional limit. So 1/2 for initial, it is equal to, you can see this is 450 and strain is 0.06. So I can write 450 megapascal multiplied by 0.006 millimeter per millimeter. So when you solve this, you will get this modulus of resilience initial comes out to be 1.35 megajoule per cubic meter. Now this is the amount of strain energy per unit volume absorbed till the proportional limit for the initial loading. Now for the final loading, when this loading reaches to a load of 600, clear, so we will find the modulus of resilience for final load. So that will be equal to 1/2 stress will be 600 megapascal, clear, and the strain at 600 megapascal is 0.008 millimeter per millimeter. Let me show you. Here you can see the stress is 600 megapascal, and here we have the strain. Our area under this stress strain curve is, this strain is 0.008 that we have calculated over here. You can see this is the strain under the stress strain curve. Okay, so we can write it will be equal to 2.40 megajoule per cubic meter. So I can write it, resilience for final is equal to 2.40 megajoule per cubic meter. Now what does this means? So we will, I do not have the space here to write, but we can see that by comparing these two modulus of resilience, we can say that effect of strain hardening the material has caused an increase in the modulus of resilience. So from this graph, you can also conclude that area under this graph will give you the modulus of resilience, and area under this graph will also give you the modulus of resilience. So in this case, the modulus of resilience has been increased. But on other hand, you can see if you take this graph, so this area under the stress strain graph will give you the modulus of toughness, clear? And for this graph, the modulus of toughness is this one. Now, when you remove this load, so you can see when you remove this load, so the modulus of toughness is going to decrease for this load. So before applying this 600 load, the modulus of toughness was this one, and when you applied this load and you remove this, so modulus of toughness is now decreased. So one thing is that modulus of resilience is increasing and modulus of toughness is decreasing. And that was all about this example 3-2. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 3.3 that is taken from chapter number 3, Mechanical Properties of the Materials, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement of the problem is an aluminum rod shown in figure 3-20A has a circular cross section and is subjected to an axial load of 10 kN. If the portion of stress strain diagram is shown in 3-20B, determine the approximate elongation of the rod when the load is subjected. Take aluminum, modulus of elasticity of aluminum is 70 gigapascal. So you can see this is the rod, that is step rod having 10 kilonewton load, tensile load. The diameter of this portion AB is 20 millimeter, while the diameter of portion BC is 15 millimeter. And this is the stress strain diagram for this aluminum rod when it is subjected to load. So you have to determine the elongation, change a total elongation in this rod due to this 10 kilonewton load when it is applied on this aluminum rod. So let's start with the solution. So first we can see that for analysis, we will neglect the localized deformation at the point of load, as well as we will neglect the sudden change in the cross-sectional area at this point, because at this point we will have stress concentration. So we will neglect them and we will find the stresses in this both portion AB and BC. So let's start with the finding the load in portion AB and BC. So I will cut the portion AB. So I will write it for portion AB. If I draw the free body diagram, so this is the rod. So at this point we have 10 kilonewton load. Clear? So here what will be the load? Let this load is P. So by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So minus 10 kilonewton plus P is equal to 0. So from here you will find that this P will be equal to 10 kilonewton. Now what we will do is that we will find the same load for portion BC. And for portion BC, you will cut this portion BC and draw the free body diagram. So it will be like the same. Here you have a load of 10 kilonewton. Clear? So here this load will be equal to, let this will be equal to PBC. I can write it over here to differentiate PAB. So we will find this PBC by using this equation, and it will give you the same, that minus PBC plus 10 kilonewton is equal to 0. So from here you will get this PBC will be equal to 10 kilonewton. Now you know that both rod is having the same load, that is 10 kilonewton load. So what we will do is that we will find the stresses in portion AB and BC. So first we will find for portion AB, we can say that stress in AB will be equal to PAB divided by area of AB. So PAB is this one, you can see this is 10 kilonewton. So 10 into 10 raised to power 3 will give you Newton divided by area. So you can see diameter of this is given as 20 millimeter. So this diameter in meter will be equal to 0.02 meter. And what we can write is pi diameter is equal to pi by 4 d square. So d is 0.02 square. Okay. So when you solve this, you will get 31.83 into 10 raised to power 6 Pascal. And when you solve it, and you can write it as that 31.83 megapascal. This is the stress that is generated in portion AB. Now for portion BC, we can find stress in BC is equal to load PBC divided by area of BC. So you can see this is the load PBC, which is again the same 10 kilonewton. So 10 into 10 to the power 3 will be Newton divided by the diameter of this rod is given as 15 millimeters. So it is 0.1015 meter. So area is pi by 4 d square. So pi by 4 0.015 square. So when you solve this, you will get stress will be 56.59 into 10 to the power 6 Pascal. And in megapascal, this stress in portion BC will be equal to 56.59 megapascal. Now you have this stress. So what we will do is that from stress strain diagram, you can see the yield stress is 40 megapascal. So I will write it from stress strain diagram. Sigma yield is equal to 40 megapascal, and you can see that sigma AB is less than sigma yield. Sigma AB was 31.83 megapascal, and that is less than 40 megapascal. So mean that portion AB is in elastic region. So what we can see, we can write it that here we know that stress in AB is equal to E into epsilon AB, because this is in elastic region. So we can apply Hooke law. So what we will get is that strain in region AB will be equal to sigma AB divided by E. So put the value sigma AB is 31.83 into 10 raised to the power 6 Pascal. And what is E? So E is given as 70 gigapascal. So I can write 70 into 10 raised to the power 9 Pascal. So when you solve this, you will get this strain in portion AB. Strain in portion AB will be equal to 0.0004547. You can also write millimeter per millimeter, or this is simply just a number. Now, for portion BC, we can see that for BC, we can see that stress in BC is greater than sigma yield. Clear? So this is in plastic region, and you can see that this is in plastic region. This is sigma BC, that is already shown over here. So we cannot apply the Hooke's law. So what we will do is that we will take the value of strain for this sigma BC, and this is strain BC is equal to 0.045. So from stress strain diagram, this strain BC comes out to be 0. Let me check it. 0.0450. 0450 millimeter per millimeter. Now for finding the approximate elongation, so I will write it. The approximate elongation in the rod will be equal to delta, and that will be equal to sum of epsilon into length L. So I can write for epsilon AB into length of AB plus epsilon BC into length of BC. So delta will be equal to epsilon AB is 0.00004547 multiplied by length of AB, which is 600 millimeter or 0.6 meter. Okay. You can also write in meter, but I will take here 600 millimeters. And plus epsilon BC was 0.0450 multiplied by length of BC was 400 millimeter. So 400 millimeter. So when you solve this, you will get total elongation in this rod when subjected to a load of 10 kilonewton will comes out to be 18.3 millimeter, which is the answer of our this question. So due to this loading of 10 kilonewton, you will see that there will be elongation of 18.3 millimeter occur in this aluminum rod. And that was all about this example 3.3. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. In this video, we are going to solve example 3.4 that is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by RC Hibbeler, and it's 9th edition. So statement is a bar made of A36 steel has dimension shown in the figure. If axial force P is equal to 80 kilonewton is applied to the bar, determine the change in its length and change in the dimension of its cross section after applying the load. The material behave elastically. So you can see this is the bar. Clear? And its length is 1.5 in the direction of Z. Its width is 100 millimeter and thickness is 50 millimeter. So this is the cross section. This is the dimension of this cross section, and P load is applied in the direction of Z. So you have to determine the change in length in the direction of change in the length in Z direction. Also, you can see due to this load, this thickness will reduce and this width will also reduce. So you have to determine the change in length in direction of y-axis as well as change in this width in the direction of x-axis. So let's start with the solution. So what will be the first step is that you can see this P is equal to 80 kilonewton is applied over this cross section. So area will be equal to, this is rectangular, so this width multiplied by thickness will give you area. So 100 millimeter in meter is 0.1 meter, and thickness is 50 millimeter, which is 0.05 meter, and it will give you square meter. Clear? Now we will first find the normal stress. Normal stress is equal to sigma, which will be in the direction of Z. So therefore I am writing sigma Z is equal to P divided by cross-sectional area. So P is 80 kilonewton. So 80 into 10 to the power 3 Newton divided by this area, which is 0.1 multiplied by 0.05 square meter. And when you solve this, you will get sigma Z will be equal to 16 into 10 to the power 6 Pascal. Now we have this stress. Now we know that also this sigma Z is equal to epsilon Z multiplied by modulus of elasticity of this material, which is A36 steel. So we do not have this E value. So how we'll get this E value? So you can get it by using this book. So at the end of this book, you can go to the property tables and you can see the average mechanical properties. Now you have this table. From this table, you can check it. A36 steel. So its E value is 200 gigapascal, and we will also take the Poisson ratio value, which is nu. So this nu will be equal to 0.32. So I will write it over here that from average mechanical properties table, we get E of steel is 200 gigapascal, 200 gigapascal, and Poisson ratio Poisson ratio, which is represented as nu, and that nu was 0.32. Okay, so you have this E value. So using this equation, you can see that strain in Z direction is equal to sigma Z divided by E of steel. So you can have both the values. Sigma Z is 16 into 10 to the power 6 Pascal, and E is 200 gigapascal. So 200 into 10 to the power 9 Pascal. So when you calculate it, you will get strain in Z direction comes out to be 80 into 10 to the power minus 6. Either it will be dimensionless, or you can see millimeter per meter or meter per meter. So this is the value of strain in the Z direction, or in the direction of the length. Now what we will find the first change in length, which is original length is 1.5. So change in the length in Z direction. We know that strain sigma Z is equal to change in length in Z direction divided by original length Z. Clear? So from here, this change in length in Z directions comes out to be epsilon Z multiplied by original length, which is LZ. So sigma Z, epsilon Z is 80 into 10 to the power minus 6 multiplied by this is length in Z direction. So I can write it, this is 1.5, so I can multiply it with 1.5 meter. So when you solve this, you will get change in length in Z direction comes out to be 120 into 10 to the power minus 6 meter, or delta Z comes out to be 120 micrometer. So this is the change in length of this bar. Now what we will do is that we will move toward finding the change in length in X direction and change in length in Z direction. As I have told you that due to this load P, there will be increase in length in Z direction, but this will cause decrease in this thickness and decrease in this width. So that can be obtained by using another formula, and we know that this Poisson ratio is equal to minus strain in lateral direction divided by strain in longitudinal direction. So again, I will show you that the strain in Z direction is longitudinal strain, and strain in the lateral, that is perpendicular to this longitudinal, either in Y direction or in X direction, will be the lateral strain. So from here we can write that we are going to find out this this lateral strain. So we can see that this lateral strain will be equal to minus nu times longitudinal strain, which is now longitudinal strain, which we have find out this longitudinal strain is equal to epsilon Z, and this lateral strains are epsilon X and epsilon Y. Epsilon X and epsilon Y, and both are equal. So we can write this, that this epsilon X is equal to epsilon Y is equal to minus nu times epsilon Z. So you have both the value. Epsilon is taken from this table, which is 0.32. So minus 0.32 multiplied by epsilon Z is this one, which is 80 into 10 to the power minus 6. Okay. So when you solve this, you will get value will be minus 25 into 10 to the power minus 6, and the unit will be a meter per meter. Clear? And that will be minus 25.6 micrometer per meter. This is epsilon X and is equal to epsilon Y, strain in lateral direction. Now for finding changes in the dimension of cross section, or we know that this epsilon X is equal to change in direction of X divided by original length of this X. So this change in length of X will be equal to epsilon X into Lx. Epsilon X is minus 25.6 into 10 to the power minus 6 multiplied by Lx. So length in Lx direction is this one. This is Lx, which is 100 millimeter, or this is 100 millimeter is equal to 0.1 meter. So I can write 0.1 meter. Okay. So when you solve this, you will find the change in length in X direction of the cross section, which comes out to be minus 2.56 micrometer. Similarly, you can also find this change in length in Y direction is equal to strain in Y direction is equal to change in length in Y direction divided by original length of Y. So we can find this change in length in Y direction is equal to epsilon Y into length of Y. So epsilon Y is minus 25.6 into 10 to the power minus 6, and Ly, length in Y direction. This is Y direction. So this length is equal to Ly, 50 millimeter. So 50 millimeter is 0.05 meter. So when you solve this, you will get this change in length comes out to be minus 1.28 micrometer. So these are the answers of these questions. Okay, so this is the change in length in X direction, and these are the change in length of the cross-sectional dimension that is shown. And that was all about this problem, example 3.4. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. In this video, we are going to solve example 3.5 that is taken from chapter number 3, Mechanical Properties of Material, and book name is Mechanics of Material by RC Hibbeler, and it's 9th edition. So statement is a specimen of titanium alloy is tested in torsion and the shear stress strain diagram is shown in figure 3-25a. Determine the shear modulus G, the proportional limit, and the ultimate shear stress. Also determine the maximum distance D. The top of the block of this material shown in figure 3-25b could be displaced horizontally if the material behave elastically when acted upon by a shear force V. What is the magnitude of B necessary to cause this displacement? So this is the stress, this is the shear stress and shear strain diagram for titanium alloy under the torsion that is tested, and we have to find the modulus of G, shear modulus G. We will find the proportional limit and the ultimate shear stress. And in part B, you can see this block. So there is a shear force applied at this face or surface, so you have to determine this displacement D, that this block will move due to this shear force. We also find the magnitude of B necessary to cause this displacement. So let's start with the solution. So first step is that we will find this shear modulus. So I will write it over here. Let me write it, shear modulus. So this value, this, let me write, this value represents the slope of straight line portion OA of shear stress versus shear strain diagram. The coordinate of point A on shear stress and shear diagrams are on x-axis this is 0.008 and y-axis it is 52 ksi. So we can say that this shear modulus G will be equal to, you can see this is a straight line in which shear stress is directly proportional to shear stress. So we can also state that shear stress is directly proportional to shear strain. So shear stress is equal to G into gamma, and G will be equal to shear stress over gamma. So we can write shear stress over gamma, and for point A we will find this because G is in elastic region. Okay, so put the value of this. You can see this is point A. At this point we have, at proportional limit we have shear stress is equal to 52 ksi, and at point A we have shear strain which is 0.008 radian. So you will put the value 52 ksi divided by 0.008 radian. So when you solve this, you will get this G will be equal to 6500 ksi, and this G is known as shear modulus, or it is also known as modulus of rigidity. Now we will find the proportional limit. So for proportional limit, this is the limit. Beyond this will not behave elastically. So what we will do is that, let me write first, by inspection of shear stress and shear strain diagram, this graph, the graph ceases to be linear at A. So this shear stress at proportional limit will be equal to, you can see this is your point A, and shear stress at proportional limit is 52 ksi. So we can write it at proportional limit shear stress is 52 ksi. And the last thing in this first part is ultimate stress. So ultimate shear stress is the maximum stress that this titanium bar bears under the torsion. So we can say that this value, this is the, you can see at point B, this value is the maximum value. This is TU, ultimate shear stress, and that is 73 ksi. So we can write directly that ultimate shear stress under this torsions comes out to be 73 ksi. So this is the answer of our first part. Now we will move towards second part, and in second part it is asked that determine the maximum distance D, that top of the block if material behave elastically when acted upon by shear force V. So due to this shear force, this block will displace from this position till this, so we have to find this distance D. So we will write it, but it is given that this, if the material behave elastically, so we will play in this region, in this elastic region. So let's move and we will quickly see this. We will write it maximum elastic displacement and shear force. So what we will do is that since the elastic shear strain, which is maximum elastic, let me write it, maximum elastic shear strain is 0.008 radian, and a very small angle, the top of block will be displaced horizontally. So you can see that this is the maximum shear strain in elastic region that will this titanium alloy specimen will bear under the shear stress. So we will write this clear, and we know that this is the angle, this is given as shear strain, which is the change in angle in right angle triangle. Initially it was perpendicular, but due to the application of this load it will change this angle. So this angle is known as shear strain, and this maximum shear strain in elastic region is 0.008. So what if I take tangent of this shear strain gamma, that will be equal to perpendicular over base, so d over 2. I will write it downward. So tangent of gamma is equal to d divided by 2. So from here this d will be equal to 2 times tangent of gamma, and 2 multiplied by tangent of gamma is 0.008 radian. And when you multiply this, you will get this displacement d due to the action of shear force, which comes out to be 0.016 inch. Now we have this, the answer of second part. We will find this shear force which will cause this displacement d. Clear? So how we will find this? We know that the third part is, we know that this shear stress, average shear stress, is equal to shear force divided by shearing area. So we can see that in elastic region, the maximum shear stress is this one, which is 52 KSI over this area. This is the area over which it acts. So it is 3 multiplied by 4. Clear? So we will write it that V is equal to average shear stress into area. So average shear stress is 52 KSI. So I will write 52 KSI multiplied by area is 4 multiplied by 3 inch square. Clear? So we will get this V. So when you solve this, you will get the shear force V will be equal to 624 kip. And this 624 kips shear force is necessary to move this displacement D is equal to 0.016 inch. And that is all about this example problem 3.5. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. In this video, we are going to solve example 3.6 that is taken from chapter number 3, Mechanical Properties of Material, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement is an aluminum specimen shown in figure 3-26 has a diameter of 25 mm and gauge length of 250 mm. If force of 165 kN elongates the gauge length by 1.20 mm, determine the modulus of elasticity and also determine by how much force causes the diameter of specimen to contract. Take modulus of elasticity. A modulus of rigidity of aluminum is 26 GPa and yield stress is 440 MPa. So you can see this is a tensile test specimen for aluminum. This is the gauge length, which is L0 and given as 250 mm. The diameter of this specimen over gauge length is D0, which is equal to 25 mm, and 165 kN load is applied. So due to this load, there is elongation in this gauge length, and this change in length, for example, this change in elongation is equal to 1.20 meter. So you have to determine the modulus of elasticity, and due to this load, the length will increase but diameter will contract. So you under this load, how much this diameter contracts. So we have to determine that contraction as well. So let's start with the solution. So first thing is that we have to find the modulus of elasticity, and we know that modulus of elasticity is represented as E, and this is, as we know that by Hooke's law, stress is equal to modulus of elasticity into strain. So E is equal to stress over strain. So first we will find this normal stress. So normal stress due to this force of 165 kilonewton will be equal to force which is F over A. So F is 165 kilonewton, so 165 into 10 to the power 3 Newton, and the diameter of this is given as 25 millimeters. So diameter area of cross-sectional area of this circular cross-section will be equal to pi by 4 d square. So pi by 4 and d is 25 millimeters, so in meter it is 0.025 square. So when you solve this, you will get stress will be normal stress will be equal to 336.1 megapascal. Now we'll find this, we have find out this, we will find strain. So we know that strain is equal to change in length over original length. So change in length is this one, 1.20 millimeter. So I will write 1.20 millimeter divided by original length, which is 250 millimeter. So 250 millimeter. So when you solve this, you will get 0.00480, and it will be either dimensionless or you can also write as millimeter per millimeter. Clear? Now we have both these values, so put it in this equation. E is equal to stress over strain. So E is 336.1 into 10 to the power 6 Pascal divided by strain is 0.00480. So when you solve this, you will get 70 gigapascal. So this is the answer of our first part. Now we'll move towards second part, in which we will see that due to this load of 155 kilonewton, there will be how much contraction is in this original diameter D0. So we'll move toward that contraction of diameter. Now we will find this contraction of diameter by using this equation that we know that Poisson ratio is equal to lateral strain over longitudinal strain. So we have this longitudinal strain, but we do not have lateral strain. So how we'll find this? We also know that there is an equation relationship between between modulus of elasticity Eg, which is modulus of rigidity, and Poisson ratio nu. So what is this equation? This equation is G is equal to E over 1 2 divide E divided by 2 into 1 plus nu. Clear? We have all this value. You can see G and G is given, E we have find out 70 gigapascal, so we'll find this nu. So G is 26 gigapascal, so I will write 26 gigapascal, E is 70 gigapascal, divide by 2 into 1 plus nu. Clear? And from here you will get this 2 into 1 plus nu is equal to 70 gigapascal divided by 26 gigapascal, and 2 plus 2 nu is equal to 70 divided by 26. So we are interested to find out nu. So 2 nu will be equal to 70 divided by 26 minus 2. And if you divide 2 on both sides, so you will get Poisson ratio, and it will be equal to 70 divided by 26 minus 2. Clear? And when you calculate it, you will get this Poisson ratio comes out to be 0.347. Now you have this value, you can just plug it in this. So we will get the lateral strain. So we will, from here we know that lateral strain will be equal to minus nu times longitudinal strain. Longitudinal strain is the strain along the length of the specimen. So minus 0.347 multiplied by longitudinal strain is this one, which is 0.00480. And when you solve this, you will get this lateral strain will be equal to minus 0.00166 millimeter per millimeter. Now this lateral strain is perpendicular to the longitudinal strain. So longitudinal strain will be in this direction and lateral strain will be in this direction, which is causing to contract the diameter. Now what we will do is that we will find the contraction in diameter. So contraction of diameter is, therefore we know that lateral strain is equal to change in diameter, which is delta D divided by original diameter D naught. So this change in diameter or contraction is equal to lateral strain multiplied by D naught. So minus 0.00166 multiplied by 25 millimeter will give you minus 0.0416 millimeter. So this minus sign means that there is a contraction of 0.0416 millimeter in diameter. So the diameter will contract by this amount. Clear? Which is the answer of our this second part. And that was all about this example problem 3-6. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.